There are two different ways of looking at electric forces. The first is using the methods that we've been looking at thus far, and by looking at charges and seeing how they exert forces directly on other charges. The second way of finding electric forces is to use a tool called an electric field. Charges will create an electric field which describes the environment around the charge, and then these electric fields exert a force on a charge that is placed within that field. Now, this second way of looking at things is a bit more abstract than directly calculating forces that one charge exerts on another. Electric fields are more abstract and often involve an extra step in calculation, but we will find that for some kinds of problems, using the tool of an electric field is necessary. So sometimes we don't have just individual charges, but we have a distribution of many charges that are exerting a force. And for those kinds of situations, it's far easier to find an electric field and then calculate the forces on charges placed within that electric field. Also, electric fields can be useful if you want to switch out the particle that is in a certain location and see what the new force on that new particle is. If you already know the environment, if you know the electric field in that region, then putting a new particle in there becomes a very easy task. So for finding the electric field, the direction of the electric field, because the electric field consists of vectors at every point in space. So if there is a particular point where you want to find the electric field, you are looking for a vector. And the electric field vector is in a direction that can be found by using something called a test charge. So we use a test charge so that the direction that we're finding is consistent. And the test charge that we use by convention is always positive. So basically the test charge is used to find direction of the electric field vector. So let's say we have this charge here and we want to find the electric field at this location. We place a positive test charge and look at the direction that the force would be on this positive test charge. Since this test charge is positive and this is a positive charge, we know that the force on the test charge would be away from the positive charge. So that's the direction of the force. That's also the direction of the electric field vector. So if you want to know the direction of the electric field at any point, you put a positive test charge, and it's an imaginary test charge, at that point, and see what is the direction of the force on that charge, and then this electric field is in the same direction. Secondly, we need to find the electric field magnitude, and the magnitude of the electric field only depends on the charge or charges not at the position where you are trying to find the electric field. So once again, if we consider that previous situation, we have a positive charge, and we put our positive test charge there, and then we found the electric field direction. Then to find the magnitude, we only consider the charge not at the location where we want to find the electric field. And the electric field amount is equal to Ke, Coulomb's constant, times the amount of charge, not at the location where we're finding, not our test charge, but the charge that's making the electric field here, the charge that's not at that location, and then divided by r squared, where r is the distance between the charge that's making the field and therefore making the force, and the distance between that charge and the location where we want to find the electric field. So to find the force on a charge using the electric field method, you follow these three steps. First off, you calculate the electric field from all of the other charges at that location. Then, if you have multiple charges that are making an electric field, you add the electric field vectors together. And then finally, you calculate the force that acts on the charge of interest. And the force is equal to the charge that is at the location where you just found the electric field times the electric field vector. And here we're actually using the charge including its sign because that tells us how the force vector points. So if I find the electric field at some location, so this is the electric field vector, and I have a positive charge at that location, then the force is in the same direction as the electric field. If, on the other hand, I have a negative charge at the place where I found the electric field, the force on a negative charge will be in the opposite direction to the direction of the electric field. So here's a question for you. A free electron and a free proton are placed in an identical electric field. Which of the following statements would be true? Would each particle be acted upon by the same electric force and have the same acceleration? Would the electric force on the proton be greater in magnitude than the force on the electron but in the opposite direction? Or would the electric force on the proton be equal in magnitude to the force on the electron but in the opposite direction?